This screencast discusses column notation in Excel's functions. This page reviews general notation for columns. In the data column, we have data x1 through xn. The sum of that data column, the sum of the xi's from 1 to n, appears directly below the data values, and the mean of that column appears below that. This is the x residual column. x1 minus the mean x bar, x2 minus the mean x bar appears here, and so forth. Whenever we sum all residuals, we get 0. This column is the residual squared column. So this entry squared, etc. When we sum that column, we get a quantity called the sum of squared for x, SSX, and that quantity is the numerator of the sample variance. Of course, if we would have been calling our data y's, when we get down to here, we'd be calling this quantity SSY. When we want to speak about a general residual value, we'll often talk about the ith residual value, or xi minus x bar. When we sum all the residual values, we get 0, as we did here. When we sum all the residual squares, we get the quantity SSX, as we did here. The sample variance is SSX divided by the number of data observations minus 1. And the sample standard deviation is simply the square root of the sample variance. This page involves two variable data, or bivariate data, and defines a sample coefficient of correlation. Here we have n x data values, and here we have n y data values. The x and y data are assumed to be linked. For instance, x1 might be the number of units serviced on the first service call, and y1 might be the time required to make that service call, and so forth for other service calls. Under the x and y column, we have the sum of, for example, the total number of units serviced over all of the service calls and the total amount of time spent on all the service calls. If we divide those sums by the number of service calls, we of course get the average number, or the mean number in this case, units serviced per service call, and in this case the mean number of minutes on a service call. Here's the x residual column, x1 minus x bar, x2 minus x bar, and so forth. And whenever we sum the all the residuals, we get 0. And here's the y residual column, y1 minus y bar, y2 minus y bar, etc. as we go down the column. And again, it's just another name for residuals, x's or y's. Whenever we sum a column of residuals, we get 0. Here's a column we haven't talked about so far. It's a column of products of x residuals and y residuals. X residual times y residual for the first data point. X residual times y residual for the second data point, and so forth. When we sum the column of x residuals times y residuals, we get a quantity called SSXY, and SSXY will be the numerator of the correlation coefficient. Here's another way of saying SSXY. Here are the product of the x residuals times the y residuals, and here we're summing from the first residual, the first data value, to the nth data value. The sample coefficient of correlation is defined as SSXY divided by the square root of SSX times SSY. You may recall the correlation is always between -1 and +1. Interpreting the correlation coefficient, The correlation coefficient at exactly 1 says the X and Y data are related linearly with the slope of that relationship being positive. Going down to the last option here, when the correlation coefficient is -1, again, the Y and X data are related linearly, except now the slope is negative. When the correlation coefficient is 0 or near 0, there is no linear relationship between the X and Y data. And by the way, that doesn't say there isn't any relationship, just no linear relationship. Here's a little guess the correlation exercise. You might want to pause the screencast, kind of guess the correlation in these three scatter plots, and then restart. In this scatter plot, you could see a straight line with a positive slope fitting this data. And so you might guess R is close to +1, maybe 0.8. In this scatter plot, you can see a straight line with a negative slope to estimate this data. So you might expect R to be close to -1, like maybe R is -0.8. And here is a scatter plot with data that's clearly related, but not linearly, maybe through some quadratic expression. And since R measures the amount of linear relationship, a good guess here would be R is 0. On the next page, we have a numerical example of what we've discussed so far. We'll compute the standard deviation and correlation coefficient in this example. Here are 5 months worth of data, month 1 through month 5. This column involves the monthly advertising expenditures in thousands of dollars, and this column involves the monthly sales revenue, also in thousands of dollars. So for the first month, for example, there was $2,000 in advertising expense and $3,000 in sales revenue. 2, 3, that's this point down here on the scatter plot. The next month, $1,000 in advertising expense and $4,000 in sales revenue. $1,000 in advertising expense, $4,000 in sales revenue. That's this month right here. The sum of the advertising expense column says that $15,000 was spent in total over the 5 months on advertising. Dividing that 15 by 5 months, there's an average monthly expenditure of $3,000 on advertising. For the sales revenue column, summing the sales revenue column says $30,000 was received in sales revenue over the 5 months, and dividing that $30,000 by 5, the average monthly sales revenue was $6,000. In this table, we make some column computations. Here is the data repeated again, with the information similar to what appears here, except we've added a row where we've named the column sums. So for example, $15,000 advertising expense is the total advertising expense, and $30,000 in sales revenue is the total revenue, and so forth. Here's the X residual column, or the advertising expense residual column. The first month's worth of advertising expenditure was $2,000. The average monthly advertising expenditure was $3,000. So 2 minus 3 is minus $1,000 in advertising expenditure. For the first month, our advertising expenditure of $2,000 was $1,000 below the average expenditure. The second month, advertising expenditure of $1,000 minus the average advertising expenditure per month of $3,000 gives us a $2,000 minus $2,000 advertising expenditure residual, saying that the second month's expenditure on advertising, the $1,000, is $2,000 below average, and so forth. And as always, when we sum a column of all residual values, we get 0. Here's the column of residual values squared. 1 squared minus 1 squared is 1, minus 2 squared is 4, and so on. The sum of the residual squared column is SSX. Here's the sales revenue residual column, the Y residual column. The first month's sales revenue was $3,000 minus the average monthly sales revenue of $6,000, puts the first month's sales revenue $3,000 below the average monthly sales revenue, and so forth. Again, summing a column of all residual values, we get 0. Here are the sales revenue residuals squared. Minus 3 squared is 9, minus 2 squared is 4, etc. Summing that column, we get SSY for the sales revenue residuals squared. And here's our new column of advertising expenditure residuals times sales revenue residuals. So we go minus 1 times minus 3 is plus 3. Minus 2 times minus 2 is plus 4. 1 times 1 is 1, and so forth down the column. Summing that column, we have SSXY is 18. We can now compute the standard deviations and the correlation coefficients for advertising expenditures and sales revenue. The advertising expenditure sample variance is SSX over n minus 1. SSX is 10. There are 5 months worth of data. Minus 1 is 4. 10 divided by 4 is 2.5. And the advertising expenditure standard deviation is the square root of the sample variance of 2.5 is $1.581 thousand, $1,581. The sales revenue sample variance is SSY over n minus 1. SSY here is 40 divided by 5 months minus 1. 40 divided by 4 is 10. Square root of 10 to get the sample sales revenue standard deviation. $3,162 as a measure of standard deviation from month to month. What kind of linear relationship is there between advertising expense and sales revenue? That's what the coefficient of correlation tells you. R is SSXY 18 over the square root of SSX 10 times SSY 40. Computing that, we get 0.9. That's a rather strong direct, that is positive, linear relationship between advertising expense and sales revenue. On this final page for this screencast, here is a simulated Excel worksheet. There's 100 data observations, and here's some formulas you can apply in Excel to compute some of the quantities that we've discussed on the previous pages. And here they are again, some of the formulas that you can put directly into a cell to make those computations. I will let you review this further if you need to. Otherwise, we'll move on to the next material.